In this week's lab, we will be using Newton's second law to study the effects of gravity and drag on a falling object from rest. For our observational setup, we are dropping a 5-gram paper ball from rest and dropping it. For a computational model, we will actually be having two this week. Our first one is dropping an object with just the force of gravity. However, both have the same initial setup for the code. We start with a mass of 5 grams, an initial position vector based off of the data in our tracker at approximately 0.003 meters, and an initial velocity of 0 in all of the axes. Our time starts at 0, and our delta t is 0.017 because of the time step of our frame rate. We will be using 9.8 meters force of gravity, and we have a j-hat vector that shows that y is pointing in the up direction. Positive y is in the up direction. Only gravity, we will be using the following code. We only have one force acting on the ball, which is the gravity force. So we use this line of code, W equals negative ball dot m times g times j hat. This is effectively just the gravity equation. The mass of the ball times gravity times j hat in the negative direction. We then set the net force equal to our variable w, and then plug it into the momentum principle, as we did last week. We will be adding the force of drag. We will be using an equation that uses the square speed of drag instead of just a linear. To do this, we use the same equation for our gravity force. W equals negative ball dot m times g times j hat. But for our force equation, we use the proportionality constant times the velocity squared. We then plug this into a vector in the y direction and then add the two together to get our total net force. And then again, we plug it into the momentum principle to get our updated velocity and position. At the bottom here, we also have code that draws arrows based on how fast and how far it has moved. If you look at our results, we have some interesting findings. Our observational model falls in between the two computational models, finishing with a final position of approximately negative 0.82 meters. The model without the force of drag falls significantly further and farther than our observed model, going down to approximately negative 1.1 meters. With drag, however, our computational model closely resembles our observed model, using a proportionality constant of 0.0009. It too ends at approximately negative point. One of the errors that could explain the discrepancy between our observed and computational model with the force of drag could be an error with the tracker software. The calibration wasn't staying consistent and I couldn't get it to quite line up. Also, the crumpled ball was not perfectly circular as the computational model assumed. What does this mean? Well, if you look at our computational models, the first one having no drag and the second one having the force of drag, and their respective velocity versus time graphs, you can see that without drag, our object continues to accelerate at a constant speed, negative 9.8 meters per second. However, with the force of drag, we experience a phenomenon known as terminal velocity, where the object speeds up linearly until it hits a certain point in which it begins to slow down. In our model, this is approximately negative. Well, if you look back at our code, the formula we used uses the square of the velocity as the drag force. That means as the object speeds up, the force of drag actually increases. Eventually, it increases to the point where it is equal to the force of gravity, at which point the object will no longer speed up or speed down. This means at terminal velocity, the force of gravity and the force of... What if we threw the object instead of letting it start from rest? Well, depending on how hard we throw the object, we see two interesting behaviors. On the left is an example of throwing the ball so that it is still faster than 0 meters per second, but slower than terminal velocity. In this case, the object follows the same pattern as rest. It speeds up at a gradually decreasing rate until it hits terminal velocity. However, what if we threw the ball faster than terminal velocity? Well, in this case, as you can see by the graph on the right, the object will slow down at a gradually decreasing rate until it slows down to terminal velocity, at which point it will stay there. This is because the force of drag is much greater than the force of gravity in that instance, so it slowly resists the movement and slows it down until the force of gravity and drag equal out,